Thanks, Susan, for this nice segue into my talk. I don't have to explain a lot of the things because she has already done it. My name is Abhishek Motayed, founder and CEO of N5 Sensors. This my talk is a little bit different. Trying to bring a perspective of a small company trying to develop an effective test program focused towards not only just technology advancement, but more like products development and market introduction. So it's a little bit different, the testing philosophy, and of course, balancing the cost, return on investment, and all that stuff. So, this morning I just made one-line introduction. This is what we do. The image on this slide is the product that we make. It's a small footprint gas sensors on a single chip, and we can actually, with this technology, we can actually produce multiple sensors on this chip, one single chip. So we talked a little bit about this, the motivation behind these nanosensors. What's driving all of us, the small, large companies, more advanced companies, why we are doing this small form factor gas and chemical sensors. Sensors have been around for a long time, electrochemical sensors. You saw this opening talk, how the sensors are being shrunk down. The reason is you have $1 billion opportunity and a game-changing applications. Think about Uber. I mean, the only reason it's possible because the inertial GPS and all that stuff, sensors in your smartphone, actually telling that there's a cab around and there's a car around, and you can actually get it right there where you are standing. There's a sensor that's actually making it possible. Same thing, your Fitbit fitness tracker. There's a inertial sensor that tells the device that whether you're moving, at what pace, things like that. So all these advanced economies and kind of products and applications you see are actually enabled by not just the computation, not the processors, but also these advanced sensors, all kinds of sensors. And of course, one sensing modality that's missing in these smart devices is environmental. A little bit of has been done in terms of pressure, temperature, and humidity. But imagine what kind of products and applications now we can start to bring and think about if we had sensors in every single phone, every single smart device in your home, outside. We talked about this morning a little bit about the data fusion and building very complex and elaborate models like multivariate analysis. But imagine now, instead of having 10,000 sensors, you have 100 million sensors. The amount of data you can develop to build this air quality models. I mean, and then just and then on top of that, for commercial companies, type of applications and products you can build on top of that using this data. It's enormous potential. So that's why there's so much interest in microsensors, low power gas and chemical sensors. So I'm not going to talk more about this. Is a little bit more technical, but this gives you a flavor into the challenges of testing sensors. So this is our sensor die. It's a bare die. It's an unpackaged die. It's a low power platform technology. You can fit in multiple gas sensors on one single chip using a patented procedure manufacturing process. And the one thing about this is it is meant to designed to operate at high humidity conditions, low humidity conditions, and a wide span of temperature. So what are the challenges as a company, small company? We are trying to make sensors for this wearable IoT consumer devices. What are the challenges? Of course, we listen to the talk about the manufacturing challenges. When you have a semiconductor manufacturing model, you not only have to consider all the yields of different processes that we heard, but also the packaging, which is one of the biggest, sort of, if not the most important issue at the end of the product, but you have to consider that while you're actually developing product, because it can literally make your product or technology useless in a commercial or a real life application. For example, you saw this image of all these packaged devices, on different packages. This is an unpackaged device. Even if it's in a different form factor, it just shows what kind of packages we can package into, but actually the package device has different components, and of course it has to have a filter membrane, a lid to put it together, and then encapsulants, dyes, wire bonds, and every single thing is a failure point. So when you're talking about testing, we talked a lot about testing, in Susan's talk, like, very detailed, thorough, but you have to understand that as a product, you're not only testing the sensors, but you're testing the fully packaged device. And in our experience, this goes through cycles of iteration. Testing sensors, sometimes the results actually don't translate when you have a fully packaged device, because guess what? There are compounds that you use to mount this dyes on the package. Those compounds are chemically sensitive. Like if you put it in different chemicals, they react very differently, that you have no idea. I mean, unfortunately, we don't have a CAD software that you can put in all these things and just spit out that, okay, this package using these type of glues and everything is going to work nicely in a chlorine environment. Unfortunately, we don't have that yet. I wish we did. I mean, so it will save us like, a few years of development time and lots of money, but that's not the case. So the only way you can do that is actually build some prototypes, test this as best as you can in different operating scenarios you can come up with, not come up as in not in your imagination, but actually talking to customers, develop the test plans like Susan said, and then validate it, and through over time iterate and develop more and advance the the state of the art. The other challenge is, just give you an example. You see the image there? That's not a cartoon. That's actually our production process runtime log, which shows the number of dyes you get just from a 4-inch wafer. So this is about 600 dyes, which is on a finger, 600 of them, and each die has about 24 connection points. And of course you have the yield and all that, and then you add the packaging, the yield drops a little bit. So you can test the fully packaged device, but in order to fully package them, because you're investing money in packaging them, you have to even test pre-packaged in a wafer, at a wafer scale. And imagine the problem of testing gas sensors on a wafer. Things like that does not exist. So we have to develop like certain kinds of testing that would be compatible in a semiconductor fab line, which can do a very fast turnaround measurement, one spot that says this die is good enough to be packaged. It falls under this Gaussian curve of like acceptable performance. So it goes into package, and then every single package has to go through 100% testing for it to be sellable. So there are challenges. Anyways, I'm not going to go over the design of the sensors, but it's just it's basically a 2-terminal resistor. It's a chemi-resistive architecture. So the way we design the selectivity is through different combinations, material combinations. So we talked about designing sensor test beds. You saw so much thoughts and considerations go into it, from reliability, analytical, validity, and all that things. There's actually another bigger concern. I mean, not bigger. I mean, really, significant also, from when you're doing it from a startup or a small company, is cost. So that's number one. And then of course it has to be accurate and reliable. So otherwise you won't be able to have confidence on your measurement and kind of, as you said, transfer the calibration. You have to ensure that the things that you did on January, the test lot, and what you did in December, they're the same, because there is no drift in the measurement system itself. There is no degradation, things like that. And the third one is effective. Effective, when I say effective, what I mean by is this system is able to produce, as I said, most conceivable operating conditions. When I say conceivable is when you talk to the end user, they say, okay, can you produce a stream of CO and CO2 with 95% RH, and then you have methane 5%, things like that. I mean, name anything. Sensor testing is a beast, because every test that you're developing is one of a kind. And it's literally unlimited number of permutations and combinations you can think of, and that you can, sort of apply to any sensor, any basic sensor. Just take a CO sensor. I mean, the amount of tests you can do to kind of get all the data that anybody would want, it's just mind blowing. And then if you're developing a single chip that has 4 different kinds of sensors, and that needs to operate at 95% RH at different, like 10 different interfering gases, you can imagine the complexity of the testing. So you have to have a system that's versatile enough to be able to adapt to different testing conditions, on a fly. I mean, tomorrow you want to test with gas A and interference C at the different mixture levels, concentration levels, things like that. The other thing that's also important for a company is that it has to be high throughput, because you got an idea. 600 dyes come out from one wafer, and we usually run a wafer lot size of 5 wafers. By foundry standard, this is minuscule. I mean, to you, it looks like a big number, but not even TSMC, even a small foundry, this is small. So imagine when you go to a volume production, the challenges of sensor testing. So even in our lab, we have to have a system that is able to test multiple sensors very rapidly. So you have to consider the gas flows, things like that, because as Susan mentioned, dwell times in your chamber and also in your packaging setup, everything becomes very important. And of course, upgradable for future projects and programs. So this is kind of like kind of the list of must-haves in a sensor test bed when we were developing our own test bed. The other thing is, when you consider cost, you have to think about whether we want to buy turnkey systems. You saw some of the images of in Susan's presentation, where you have some turnkey systems like the zero air generator, and some, of course, highly custom built equipment that takes a lot of machining, design, and things like that. There's a trade-off between time, money, and what are you actually trying to accomplish. So in terms of kind of versatility and able to adapt to different test conditions, like profiles and things like that, here's an example. That's the system that we are trying to design, what it has to do in terms of adapting to different things. Here you see a sensor package, which is a very old school DIP package that we developed in 2015, rapid testing. Then it's a 2016, come down in 1 year, we have a package which is a QFN, standard plastic QFN package. And then on your right hand side, you see a fully assembled detector. I mean, you can call it a prototype detector with onboard electronics and everything. Of course, it has a housing, but it has been taken out to show you the electronics. And there's an app, like a Bluetooth module, all embedded in it. And the system has to be able to test anything in between, starting from that and to that and anything in between. So you imagine the challenges of developing a test system for a company, because we don't know what the product is going to look like 2 years from now, especially when you're starting on the first early days. Of course, once you get more advanced, you know how the product is going to look like. But guess what? You have a sales pipeline, a product pipeline. Things change. So you have to have a system that you have to be able to adapt and modify, on the fly. You can't have a system that's downtime of 3 months to modify. Our downtime is usually 2 weeks, and then we can modify, add things like that. So this is, kind of our test bed. It's pretty crowded. You're more than welcome to come see us, see this facility. I mean, it's pretty neat. It doesn't get below, get down to the levels of parts per trillion, things like that, because we are not into explosive sensing, not trace sensing, but more like fire gas, consumer applications, where the levels are kind of in ppm range. So this bench has a very unique capability, and this is all designed and installed by us and maintained and upgraded by us. So it has 2 different manifolds, one for corrosive gases, what Angela program is funding us for, and then the other side is non-corrosive gases like carbon monoxide, dioxide, simple gases. This side, the left-hand side, is things for chlorine, hydrogen chloride, hydrogen cyanide, NOx, SOx. Separating that out ensures that if something happens on the corrosive side, there's a safety precautions and all that. They have, filters, inline filters in every single, line, tubing, valves, emergency relief valves, things like that, and alarms. And then we have the ability to also sample gases in the stream through compressed tanks, also from a bubbler. and then also there are different other ways to generate the vapor, and we have the ability to mix simultaneously 8 gases in any carrier gas we choose: air, normal air, high purity air, nitrogen, oxygen, and a ratio of nitrogen and oxygen. So it allows you to test a sensor in oxygen lean and oxygen rich conditions. And we have a Bronkhorst humidity generator, so inline generator, so we can actually produce accurate humidity set points in the mixed gas stream all the way up to 90%. And we have inline humidity monitor. As Susan said, it's very important to measure what's coming out from your test bed to ensure that you have valid sort of stream, valid test conditions. So we have inline testing, and we have ports to pull out samples to send out for GC mass spec analysis to give us the sampling, quantification of the sampling, because we don't have a GC mass spec in our lab. So anyways, and it's computer controlled, so you can develop test plans, run them automatically overnight, things like that. So developing a test plan from a company is a little bit challenging, so because you have some products or some technologies that are in early stages where you need more qualitative yes or no type decision, and some are more later stages where you need very comprehensive data, statistically relevant data, to produce a spec sheet that you can actually give it to the end users. And there you have to be very careful. So when we talk about developing test plans, we have this in mind, that one side you have very quick, fast turnaround tests which says this design is going to work, no, scrap the design, improve it, or don't worry, go move to the next design. The other one, once we have refined the design, now you start the more quantitative test plan. So I'll just quickly go over how the philosophy about developing effective qualitative and quantitative test plans. In qualitative test plans, if you're just trying to figure out if this design is going to work or not, what we do is we figured out that we can actually expose it to a library of molecules going from oxidizing to kind of, we call this as a test library, probe molecules, oxidizing, reducing, and some few in between points. Gives us a quick snapshot of how the sensor is going to respond in different gas conditions, and then from there we can quickly iterate, yes or no, move back. And then obviously quantitative testing is more detailed. Once we have finalized the design, then as Susan said, we go through tier testing. Tier 1 is more simple. You pick the span, because you're trying to measure, or you're trying to determine all the characteristics that Susan listed, detection limit, quantification, and all that stuff. So you break it down into tiered approach so you can get data fast. So if you need to do final adjustment, you can do it before you take more extensive tier 2 testing, which costs money because it's a lot of overhead in testing. So I'm not going to go through them, but you can see it gets more complex as you go into second tier, third tier testing, because you have to consider not only just the performance of the sensor, but reliability. Believe it or not, I mean, even the best sensors will have drift, so we have to take into the consideration. And we talked about the the lifetime accelerated testing, things like that. So this comes into picture. It becomes an integral part of your testing plan as you move farther and farther into the product development. So I guess with that, this is the last slide. It just shows some example of sensor testing and some of the data that you can collect and format a table, things like that. This is a hydrogen sensing going on for 12 hours unattended, and then hydrogen sensing, like pulses of hydrogen sensor recovery, things like that, that you can estimate the characteristics that we have seen in the previous talks before. So this is, by that I will conclude my talk. Thank you very much for your time.